Okay, today we're going to look at solving logarithmic equations, or solving equations with logarithms. So in this first example, if we want to solve for x, we can rewrite this logarithm in exponential form. Okay, so we can write our base, which is 6, to our power of 2 is equal to x. Okay, so then we've got our base of 6 to our power. Remember, the power, the exponent is on the opposite side of the equal sign of the logarithmic equation. So when it's in logarithmic form, we've got our power on the other side of the equal sign. So base of 6 to a power of 2 is equal to this value, x. We know 6 squared then is equal to 36, which actually simplify this a little more. So 36 equals x, or x equals 36. Okay, so really we're trying to figure out 6 to the power of 2, so 6 to the power of 2 is equal to what? 36. So that means log base 6 of 36 is equal to 2. This is our solution, x equals 36. Okay, next example, again, we're going to rewrite this problem in exponential form. So we've got our base of 5, our exponent, when we're dealing with logarithmic form, is on the other side of the equal sign in logarithmic form, and that's going to be equal to 1 over 25. So we've got 5 to the y is equal to 1 over 25. Okay, we can write 1 over 25 also with a base of 5, that's 5 to the power of negative 2, right, because we've got 5 squared in our denominator, so 5 to the negative 2 gives us 1 over 25. So now we've got the same base on each side, and we can cancel our base then and equate our powers. So y is then equal to negative 2. Okay. So basically when we're solving this, we can think in our heads 5 to what power gives me 1 over 25, and that's y equals negative 2. Okay, so we can set this equal to x, and we've got our base equal to 3, so 3 to the power of x is going to be equal to 27 if we rewrite this in logarithmic form. Well, I wrote it as y here. So okay, so we've got this in exponential form. 3 to the power of y is equal to 27, and we can write 27 with a base of 3, and we know that's 3 cubed, so 3 to the power of y is equal to 3 cubed. We've got the same base on both sides, so we can cancel our base and equate our exponents. So y is equal to 3. And if we were doing this in our head, we would be thinking 3 to what power gives me 27? And that, of course, is 3. 3 cubed gives us 27. Okay, here we're evaluating this logarithm. Again, we can set it equal to some variable, either x or y. So log base 7 of 7 squared is equal to y. Then we can rewrite it in exponential form. So we've got our base to our power is equal to 7 squared. So 7 to the y is equal to 7 squared. Notice we've already got the same base on both sides, so then we can cancel our bases of 7 and we equate our exponents. So y is equal to 2. So this is a really, really important shortcut that you should recognize. Look, if we have the same base as we do here, it's actually going to be equal to whatever that power is. 2. So it's a shortcut you can apply. So you don't even have to go through all this work. It's totally fine if you want to, but just so you recognize that shortcut. So this is equal to 2. So because we have the same base here, we'll just get it equal to our exponent, whatever this value is. Okay, we're going to solve this logarithmic equation. We're going to write it in exponential form first. So so we've got, I wonder if you can even see it. Not really. Okay, we've got our base of x to our power 2 is equals to 16. So x to the power of 2 equals 16. So in our heads we're thinking, what squared is going to give me 16? Squared equals 16. So we can take the square root of both sides, and you have and x equals 4. And you might be thinking in your head, hey, wait a minute, x equals positive or negative 4 because we took the square root of both sides. But actually, when we're working with logarithms, we want to always keep our base positive. Okay, so this value, this x, is always just going to be positive. So when we square root both sides, x is just equal to 4. Okay, so that's our final solution there. Okay, again, we want to solve for x, so we can write this in exponential form. So we've got our base to our power is equal to 81. So x minus 1 to the power of 4 equals 81. Okay, so we're going to take the fourth root of both sides, or we're thinking what times itself 4 times is going to give me 81. Okay, so we know 3 times 3 gives us 9, and 9 times 9 gives us 81, right? So 3 times itself 4 times gives us 81. So we're taking the fourth root of both sides, and we'll get x minus 1 equals 3. That's the fourth root of 81, or 3 times itself 4 times gives us 81. And again, because we're using an even root, often we would use a plus or minus here, but because we're dealing with a base, our base with logarithms is always going to be positive. Okay, yeah. So x minus 1 is equal to 3. We're just going to add 1 to the other side, and we'll get x equals 4. Okay, and that was okay. Yeah, another way to think about it, instead of taking the fourth root of both sides, is how can we write 81? What to the power of 4 is going to give us 81? So 3 to the power of 4, that's another way we could have done it. Okay, next one, again, we're going to write this in logarithmic form to solve for x. So we'll have 2 to the power of 5 is equal to x plus 4. Okay, we know 2 to the power of 5 is 32. We can subtract 4 from both sides, and we get, what is that, 28. Okay, so x is equal to 28. Okay, so here we want to evaluate, we've got 4 to the log base 4 of 16. This is all part of our power. And to evaluate this, we can first make it equal to a variable. So we can make it equal to y. Okay, then we can rewrite this in logarithmic form. Okay, so we've got a base of 4. Our power, which is going to go on the other side of the equal sign, is here. And then we're going to have log base 4 of y is equal to log base 4 of 16. Okay, so this goes here, base of 4. We've got 1 on the other side of our equal sign of our exponential equation, so that goes here. And our power goes on the other side of the equal sign of our logarithmic equation. Okay, so now that we have log of the same base on both sides, we can actually cancel our log of that same base. Okay, so we can equate these values. Y is then equal to 16. That's a new rule that we'll look at. So y is equal to 16. Okay, another shortcut that you should recognize is if this number is the same, you have log base that same number, so this is going to equal just 16. That's what we got here when we did all that work. So you can use that shortcut all the time. You don't even have to do all this work, but it's important that you recognize, where that's coming from. And if you want to do that work, that's totally fine. So if this number, the base of your exponent, is equal to the base of your logarithm that happens to be in your power, then whatever this value is going to be what it's equal to. Okay, some practice. Let's see, we'll do this first one here, letter A. We've got, here are the solutions. Okay, we've got 2 to the power of 3 when we write this in exponential form. 2 to the power of 3 is equal to x. And we know that 2 cubed is equal to 8. So for letter A, x equals 8. For letter B, again, we can write this in exponential form. So we've got our base of 4 to our power of 1/2 is equal to x. So 4 to the 1/2 equals x. Remember, 4 to the 1/2 is the same as the square root. So x is going to be equal to the square root of 4, which is equal to 2. So x equals 2. Okay, another thing about logarithms. And I will repeat this later, so if you don't want to make a note of it, that's okay. But this number, whatever we're taking the log of, absolutely has to be greater than 0. So it can't be 0, it's got to be positive. So when we take the square root there, it's not correct to say plus or minus 2. It's just going to be a positive 2. And I'll show you why that is in a future slide, just a minute here. Okay, this next one. We've got x to, when we rewrite this in exponential form, x to the power of 4 equals 81. Okay, we know 81 is 3 to the power of 4, we just looked at that. So then x, of course, we can equate our bases. X has to equal 3. This next one, we've got our base of 2 to the power of 3 equals x minus 6. We know 2 cubed is 8. We can add 6 to both sides, and we get x equals 14. Okay, letter A, it's good for you to keep practicing this, I think. So even though we know that this is one of our properties, that if this is the same base here and here, it's going to cancel and we just get n. We should be able to understand why that's happening. So if we want to prove this, we're going to take log base a of a to the n equals n, and we're going to rewrite it in exponential form. So when we do that, we get this base, so a to the power of n, so a to the power of n is equal to this value, a to the n. And that's true, right? A to the n equals a to the n. So we've proved it by showing that two things are equal. So when we rewrite this logarithm in exponential form, we get this. Actually, we want to show that it's equal to n. So a to the n equals a to the n, and hence we can equate our powers then. So n is equal to n. Okay. Next, we want to evaluate some of these logarithms. So we can say, okay, this is equal to x. So 4 to what power gives me 16? Okay, so our base of 4, our power of x equals 16. In our heads, we're thinking 4 to what power gives me 16? And of course, x is going to be 2. 4 squared gives us 2. If you didn't realize that right away, we can can rewrite 16 with a base of 4, and then we can cancel our bases, and we get x equals 2. Okay. Some more difficult ones. Let's see this one here, number 6. So let's set that equal to x. So in our heads, we're thinking 5 to what power is going to give me 25 square root of 5. Okay, 25, let's write that as a base of 5, and the square root of 5, let's write that as a base of 5. So a bit of review of exponents here. So we've got 5 to the x, 25 is 5 squared, the square root of 5 is 5 to the 1/2. Remember, when we have the same base with exponents, we add our exponents. So we've got 5 to the x equals 5 to the 2.5, or you can write that as 5 over 2. Okay, so then we've got the same base on both sides. We can equate our exponents. So we have x is equal to 2.5, or x is equal to 5 over 2, either one. Let's do a couple more like those. Number 7 here. Let's make that equal to x. So we'll have our base of 3 to the power of x equals 1 over the square root of 3. 3 to the x equals 1 over the square root of 3. So 1 over the square root of 3, we need to rewrite with a base of 3. So we've got 3 to the x equals, okay, we've got a square root, so that's going to be 1/2, and it's in the denominator, so our power is going to be negative. So 3 to the 1/2 gives us the square root of 3. 3 to the negative 1/2 gives us 1 over the square root of 3. So that's, it's reciprocating it. Okay, we've got the same base on both sides, so x then is equal to negative 1/2. Okay, maybe just one more. So this one is just like, well, not exactly. It's similar to this one here. Okay, so number 8, we're going to make this equal to x. Just quickly. Oh. Okay. Good. So we've got 4. We've got a base of 4 to the power of x is equal to this 1 over 2 square roots of 2. Okay. Let's combine 2 square roots of 2 in the denominator. So we've got 4 to the x equals 1 over, so let's write these powers of 2. This is 2 to the 1 times 2 to the 1/2. Okay, so we've got 4 to the x equals 1 over, when we add those powers, because we're multiplying with the same base in the denominator, we've got 2 to the 3 over 2. 4 to the x, let's write that with a base of 2, so we'll have the same base on both sides. So 4 is 2 squared to the x. And 2 to the 3 over 2, if we want to bring that up to the numerator, we're going to have to write that as a negative power. So 2 to the negative 3 over 2. Remember, all that negative power does is it just reciprocates our exponent, so, or it reciprocates our base of 2. So we'll have 1 over 2 to the 3 over 2 when we do that. Okay, here we're going to multiply our exponents because we have a power to a power, so we have 2 to the 2x equals 2 to the negative 3 over 2. So now we finally have the same base on both sides. We can equate our exponents. So 2x equals negative 3 over 2. When we divide by 2, it's the same as multiplying by 1/2. Remember, dividing by 2 is the same as multiplying by 1/2, multiplying by the reciprocal of 2. So 2 over 1 goes to 1/2. And we get negative 3 over 4. Okay, that was a tough one. Good. Okay, logarithmic equations. We looked at this just very briefly in which example was that? This one here. So I said we could cancel our logs on both sides. as long as we have the same base, and as long as it's really important that there's no coefficients here. Okay, so as long as it's literally log base 4 on both sides, we can cancel our log base 4 then. Okay, so in this case, if we have log base 3 of some value, we can cancel that on both sides, and it's just x1 is equal to x2. Okay. Yeah, I'll show you one last example of that. So logarithmic equations, when we solve these, we want to isolate it to a single log term. Okay, so notice here, first of all, we definitely need to get log on this side first, and we have to combine these logs into a single term. We can't have any coefficients and we can't have any plus. It needs to be one single log, okay, on both sides, and they have to have the same base. Then we're going to convert it to an exponent. So I'll show you that, and then solve the equation. Okay, so first of all, let's get this 2 as a logarithm. Remember, when we don't write the base, we're working with base 10. So this is log base 10. So we're thinking, okay, we've got log base 10 of some value is equal to 2. Okay, so in other words, 2 to the power of 2, or sorry, 10 to the power of 2 is equal to x. Okay, so 10 squared is equal to x, so that's 100. Okay, so this is 100. So log base 10, I'm just going to write the right side here. I'm going to replace this 2 with log base 10 of 100, because that is equal to 2. Okay. On the right side, remember, when we're adding logs with the same base, we can combine them into one log with multiplication. So log base 10 of x times x minus 15. Okay, so now we've got the same logs, a single log with the same base on both sides. So we've done this. We've isolated it to a single log term. We've combined this addition into multiplication and have turned it into one single log. We've got the log with the same base on the other side. Convert it to an exponent. What that means is we can do 10 to the power of on both sides, and remember that's going to cancel this. So that's the reason we can cancel the logs on both sides when we're working with logarithmic equations. Okay, and then it's just up to us to solve the equation. So we're going to distribute x here. We've got x squared minus 15x is equal to 100. We can get everything all on one side. So x squared minus 15x minus 100 is equal to 0. And we can factor. So minus 20 plus 5. That when we multiply those, we get a negative 100. When we add them, we get a negative 15. Okay, so we get x equals 20 and x equals negative 5. So this part is really, really important. X equals negative 5 is actually not a solution. Our only solution is x equals 20, because we can never have a logarithm of a negative number. So go back to the original equation. Look, we have log of x, and we have log of x minus 15. So when we plug in 20 here, we've got log of 20, and we've got log of 5. Those are both positive numbers. So log of 20 is totally fine. If we plug in negative 5, we've got log of negative 5, which is not part of the domain of log. We cannot take the log of a negative number. So with log of x, x has to be greater than 0. The reason we can't take the log of a negative number is because, say we have log of negative 5, which is not okay, and that's equal to whatever, some power, okay? So if we were to rewrite this in logarithmic form, remember this is base 10. So we're saying 10 to some power is going to give us a negative number. No way, it's not possible. There's no way that we can take a positive base to any power and ever get a negative number. It's just not possible. Same with 0. We can't have the log of 0. So if we have log of 0 is equal to x. Okay, so by the way, this is not possible. Log of 0 is equal to x, so this is a base of 10. So if we rewrite it in exponential form, we're saying 10 to some power is equal to 0. That's also not possible. There's no way you can take the number 10 to a power and get nothing. Okay, so this is not possible. So because of that, when we're solving these logarithmic equations, we have to check our answers. We have to make sure we're not creating log of a negative number. Okay, because when we plug this -5 back in for our x here, okay, we would get log of -5, which is not okay. And here, we would get log of -20, also not okay. So -5 is not a solution. Our only solution is x equals 5 because of the domain of log. X absolutely has to be greater than 0. It can't be equal to 0. It has to be positive. Okay, thanks, guys.